Phorbol is a natural, plant-derived organic compound. It is a member of the tigliane family of diterpenes. Phorbol was first isolated in 1934 as the hydrolysis product of Croton oil, which is derived from the seeds of the purging Croton. Croton tiglium. The structure of Phorbol was determined in 1967. Various esters of Phorbol have important biological properties, the most notable of which is the capacity to act as tumor promoters through activation of protein kinase C. They mimic diacylglycerols, glycerol derivatives in which two hydroxyl groups have reacted with fatty acids to form esters. The most common and potent Phorbol ester is 1,2-O-TETRADECANOYLPHORBL13 acetate, TPA, also called PHORBOL12-MYRISTATE13 acetate, PMA, which is used as a biomedical research tool in models of carcinogenesis. History and source. Phorbol is a natural product found in many plants, especially those of the Euphorbiaceae and Tigliaceae families. Phorbol is identified as the active constituent of the highly toxic New World tropical manchineel, or beach apple, Hippomane manchanella. It is very soluble in most polar organic solvents, as well as in water. In the manchineel, this leads to an additional exposure risk during rain, where liquid splashing from an undamaged tree may also be injurious. Contact with the tree or consumption of its fruit can lead to symptoms such as severe pain and swelling. Another plant of particular note is Croton tiglium, the source of Croton oil from which Phorbol was initially isolated. The seeds and oil of C. tiglium have been used for hundreds of years in traditional medicine, generally as a purgative. The seeds have been mentioned in Chinese herbal texts as early as 2,000 years ago and have since been used for the treatment of a variety of conditions from headache to intestinal disorders. The purgative effects of the oil are largely attributed to the high percentage of Phorbol esters contained in the oil. Although derivatives of the Croton plant have been used medicinally for thousands of years, Phorbol was only isolated from C. tiglium seeds in 1934. The structure of the compound was determined in 1967, and a total synthesis was described in 2015. Mechanism of action. Phorbol derivatives work primarily by interacting with protein kinase C, PKC, although they can interact with other phospholipid membrane receptors. The esters bind to PKC in a similar way to its natural ligand, diacylglycerol, and activate the kinase. Diacylglycerol is degraded quickly by the body, allowing PKC to be reversibly activated. When Phorbol esters bind to the receptor, they are not degraded as efficiently by the body, leading to constitutively active PK. Protein kinase C is involved in a number of important cell signaling pathways. Thus, Phorbol ester exposure can show a wide range of results. The main results of Phorbol exposure are tumor promotion and inflammatory response. Although Phorbol is not a carcinogen itself, it greatly enhances the action of other substances and promotes tumor proliferation. PKC is a key component in biological pathways controlling cell growth and differentiation. When Phorbol esters bind to PKC, cell proliferation pathways are activated. This effect greatly promotes tumors when the cells are exposed to even a subcarcinogenic amount of a substance. Protein kinase C is also involved in activation of inflammation pathways such as the NF-κB pathway. Thus, exposure to Phorbol products can induce an inflammatory response in tissues. Symptoms can include edema and pain, especially to the skin and mucous membranes. While Phorbol itself doesn't have irritant activity, nearly all Phorbol esters are highly irritant. with a wide range of ID50s. The LD50 of Phorbol esters for male mice was found to be about 27 mg per kilogram, with the mice showing hemorrhage and congestion of pulmonary blood vessels, as well as lesions throughout the body. Total synthesis. A total synthesis of N-anti-pure Phorbol was discovered in 2015. While this synthesis will not replace natural isolation products, it will enable researchers to create Phorbol analogues for use in research, especially creating Phorbol derivatives that can be used for anti-cancer activity. Previously, the difficulty with synthesizing Phorbol had been creating CC bonds, especially in the six-membered ring at the top of the molecule. This synthesis starts from ±3 carin, and uses a series of 19 steps to eventually create Phorbol. Uses in biomedical research and treatments. Because of their mechanism of action, Phorbol esters can be used to study tumor proliferation and pain response. TPA is most commonly used in the laboratory to induce a cellular response.
For example,
TPA can be used to measure response to pain and test compounds that may mitigate the inflammatory response. TPA and other Phorbol esters can also be used to induce tumor formation and elucidate its mechanism. Some Phorbol esters have shown anti-cancer activities and can potentially be used as a defense against certain viruses and bacteria. TPA, together with ionomycin,
can also be used to stimulate T-cell activation,
proliferation, and cytokine production, and is used in protocols for intracellular staining of these cytokines. Phorbol, in the form of Croton oil, is also in folk medicine as a purgative, counterirritant, or anthelmintic. Phorbols at the U.S. National Library of Medicine. Medical subject headings: Mesh.